we are going to describe the topic backtracking. Now, suppose we have a situation where we have to make some series of decisions among various choices. Now, in that case, we don't know what decision may be true, what choices may be true, but we have to find. We have to go through all these situations and then find out what is the best solution. In that case, somehow suppose we go to some decisions, at the end of that, in that choice we may find the decision is not working, so we have again to backtrack, then go to the next choices. That is the basic things about backtracking. Now we can, in technical terms, we can say it's a depth first search. It only include tree search. Actually, in a tree we can backtrack from a leaf node to a parent nodes, but if we find there are no more nodes, that is if we reach the leaf nodes, then we can only go back to the parent node, as well as we can go to the next another child of that parent. Now if we find the leaf node is the solution, then you can say it's a promising, or otherwise we can say it's not promising. In backtracking, the recursive algorithm or recursive search, the algorithm is as follows. The first thing is we test whether the solution has been found or not. For a particular choice, we first select a choice or first select a node. We test if this is solution or not. If we find the solution, we return. Otherwise, we make a choice. Again, we recursively we go try to find a solution until and unless we find the solution. Otherwise, in the end of that search, it will show it as a failure. Now we can show it as an animation. First, make it start, then the dead end. Dead end means in that end, or in that leaf nodes, there is no solution. Then we again backtrack and go to the next child of that node. Again we find a dead end. Then we go back to this previous parent. Then again we find that there is no, again one more dead end. Then and finally we get a success. That is the desired result. That is called the backtracking. Now, the real life example of backtracking is the n-queens problem, where what we do is, we suppose n-queen means there is a board of n into n cross n board, and we have to press all the queens in each of the row, and but no one can attack each other. Suppose in the n-queen problem we consider the 8-queen problem. Suppose this is a board of 8 cross 8. This is a 4 queen actually. 1 2 3 4 5 6 7 8. This is 4 queen. Or this is the 8 queen. In that case, what the solution is, in the first row we can place the queen in the 4th place, 1 2 3 4. And in the second case, if we place here, then this queen can attack this one. If we place in that place, this one also can attack. So we can place it in this way or in this way. The next, and this tree is formed. This tree is called the state space tree. Now, the first thing, can the queens placed in the board so that the no queens are attacking each other. The first place is, we cannot place in that row, in that way as well as in that way. Queen can attack in the chessboard, queen can attack in the horizontally, vertically, and the diagonally. The number of queens, n queens, so n number of row and n number of columns. Now, how the program works? We use a stack. By that stack, we can show how it works. Now, the first case, suppose first we place a queen. This is a 4 queen example. First we place a queen in the row 1 and column 1. Then next first placed it in the row 2 column 1, but in that case the first one can attack each other, one can attack each other, so we cannot place in that way. So we go to the next place, next column, again they can attack each other, so we have to place in that third row. In that case no one can attack each other. Now we go to the third step, we again place it in that first row, first column, second column, third column and fourth column. In all these cases it can attack each other, so we have to, so no solution can be found, so we go back to the previous one, that is row 2, and we place this queen to the last one, because in this, if it placed in the third column we cannot place the queen in the third row, so that's why you have to rethink the refine the solution, then place it in the last column. Then we go back to the next part, that is queen. In that way we can find out the solution. And that is the actual backtracking. And we can, in a short, we can say backtracking can be thought of this as searching of a tree for a particular goal in leaf node. All the solution can be found in the leaf node. We have to find that particular leaf node until unless we search the depth first search, but until unless we complete our search when we find the this particular leaf node. What is the success? And this is a state space tree. The pseudo code. Suppose we check node first for a particular node. If the node is promising and there is a solution at B, write the solution, else we again go to the child, and for each child we check the nodes. The procedure whereby after determining the node, this part is promising means the node can lead to a solution, otherwise it can be called as non-promising. And pruning, that we have to check each node where it is a promising or not, and backtracking to the nodes to the parent. If we don't find any promising situation, we backtrack to its parent's node. And backtracking is a procedure to prune state space tree. Prune state space tree, and that is a complete state space tree of a 4 queen problem. There is total 65. If the solution is in the 65th solution, though we can, if we generate a state space tree, there is total 65th node. So the worst case it will run up to 65 times. It is typically a very exhaustive search because we have to find out each of the row, and then we can go back to the solution. So in the worst case, the time taken, the number of nodes in the entire state space tree. So it will something like 1 plus n plus n square up to n to the power n, for a n plus n tree. So it will be, suppose n into the power n plus 1 minus 1 by n minus 1. So we can roughly say it is up to, for number of nodes checked by algo DFS it is 341. So number of candidate solutions checked in algo 2, that is for n matrix it is 24. For backtracking it is 61 number of checks. So number of node, number of promising node found is 17 for a 4 queen problem. So we can at least reduce the number of checking from DFS to backtracking. And one more part which will be graph coloring. What is the graph coloring? A graph is said to be colored, and we have to color each of the vertices of the graph, but no two adjacent vertices have the same color. And the schematic number is the smallest number required to color a complete graph. For the table graph there is a commodity number is 3 because there is only 3 colors, red, green and blue. In that case also, suppose suppose 1, 2, 3 and 4, there is 4 color, the chromatic number is 4. Now for a particular, is consider real life problem, we have to do a routine for a particular exam, suppose in a school, and there are the different number of combinations of subject taken by the students. Suppose math, English, biology, chemistry, math, English, computer science, geography. For there are, each of the student have the 4 subjects, and they have the different number of combinations. We have to find out the minimum number of exam period. We have to complete the exam in the minimum number of days, but no two exam can run parallelly, because if suppose math and English can run in a single day, then a student cannot give that exam. So we have to take that consideration. So what we do is, we first generate a adjacent matrix. That is, what is the matrix for each of the subject. We write each of the subject in the row as well as each of the subject in the column, and for a particular for each of the combination we just write what is the combinations, and based on that combination we first take and 1D array initialized with, first take a array, then we start with the first exam, the math, and then for English, if it is adjacent to this first, in for math English adjacent, that is why adjacent, because for math, if math is there, English, biology, chemistry cannot be possible, as well as computer science, geography. So for math, English, biology, chemistry, computer science, geography cannot be possible. So for math, first we say take a subject math, then English. So English cannot be possible, so number of days required is 2. Then again 3 for biology, because biology also in the same combination. 4 for chemistry, 5 for computer science, as well as 6 for the then now 4. Why geography is 4? So if I consider the first row, geography, when geography is there, biology or chemistry, geography is biology also in the same row, so chemistry and geography is not in the same row. Chemistry, geography cannot be in the same row, so we can take it as a 4. So because geography and chemistry is not adjacent, so that's why the number is 4. In that way, we find the solution. The number of the solution is 6. So we required at least 6 days to complete the solution. And here also generate a state space tree in that fashion. The time complexity to solve that problem is